This is Group 9, and we are here to talk about the fluid mechanics involved with a liquid hourglass. A liquid hourglass is dissimilar to a traditional sand hourglass in that instead of solid particles and air, we have two liquids within the glass, water and oil. When the hourglass flips, water drops down through the oil in a timely manner. But how does this work? As the saying goes, water and oil do not mix. This is very true because the density and viscosity of water and oil are quite different. Water has a slightly higher density, while oil has a significantly larger viscosity. These differences allow the water to pass through the oil while each retains its composition. Unlike many operations in fluid mechanics, we cannot apply the Bernoulli equation to the liquid hourglass. The flow is not steady and viscid, as it is not continuous and eventually comes to a stop. We can, however, apply it over short intervals to make necessary calculations for velocity at specific points throughout flow. The liquid hourglass is a perfect example of the Rayleigh-Taylor instability. Similar to, but not to be confused with, the Kelvin-Helmholtz instability, this is an instability at the interface of two liquids with different densities, the denser laying on top. The greater attractive forces of gravity on the water pull it down through the oil, and its potential energy decreases. This image shows two fluids of different densities interacting as gravity does its thing. The RT instability is depicted in the first few frames, while Kelvin-Helmholtz makes an appearance around 3 seconds in. The rate at which these disturbances grow is given by the exponential equation here, dependent on temporal growth rate and time. Temporal growth rate is the square root of the product of gravity, spatial wave number, and Atwood number, which is derived from fluid densities. In conclusion, the liquid hourglass depends on the difference in density and viscosity between water and oil. These variances create an instability at the interface between two liquids when in contact with each other. The interface is disturbed by the movement of the denser liquid traveling downwards at the same volumetric rate that the lighter fluid moves upwards. The hourglass shape provides a narrow channel for flow, which will control and slow the velocity at which the water and oil move. The consistency of this operation allows the hourglass to be used as a proper timekeeping tool.